Okay, let's start. So, good evening, guys. So, welcome to NEET World. So, in this session, we are going to continue with the physics class of NEET World. Okay, in the previous session, we were talking about the chemistry class. Okay, chemistry has been completed. In this session, we are concentrating on the physics. So, the first thing what we are going to say is, yesterday we were up to the topic the perpendicular axis theorem and the parallel axis theorem, right? And we were seeing about the problems. And last class I gave a homework on what is the moment of inertia of a ring about a tangent to a circle of a ring, right? No, so now we'll see the answer of this. Okay, so tangent to the ring in the plane of the ring is parallel to the one of its diameter. Okay, this is the first point. Yeah. So the second one what we are saying is the distance between them, that is two parallel axes are r. Okay, that is nothing but the radius. Okay, so using the parallel axis theorem, yeah, so I tangent, like moment of inertia in tangent will be equals to moment of inertia of a diameter plus m, the distance between them, that is mr square. So we know that moment of inertia about diameter is nothing but mr square by 2. So when I add both of them, what will happen? Mr square plus 2mr square by 2, which is nothing but 3mr square by 2. This is the answer, right? Take a note of this. So whoever not written the homework now, you can take, who have written, want to cross verify, you can cross verify it. Okay, and if any mistake you have done, you can Srivastav. Done? Okay. So kinematics of rotational motion about a fixed axis. So we were talking about angular displacement, which is denoted by the letter theta. Angular velocity is nothing but omega, which is equals to d theta by dt, and angular acceleration alpha is equals to d omega by dt, right now. So displacement we have talked about in linear thing, na? Like a motion in a straight line, that is s, r, x, whatever the terms, yes, no. So displacement, velocity means s by time, displacement by time. Okay, and angular, let me write here, this is s, wait a minute, displacement, and v is equals to displacement ds by dt, right now, ds by dt, whereas acceleration is nothing but dv by dt, right now. So this is about a linear thing, na? And this is the angular thing. Okay, so we were talking about the kinematic equation, right? So in the kinematic equation we have seen this equation, no? Yeah, so v is equals to u plus at, v square minus u square is equals to 2as, and s is equals to ut plus of at square, right now. This is the kinematic equation we have seen there, huh? So can we write this kinematic equation in terms of rotational thing? Yes. So they have given the things, but we'll see how we can write it. Okay, no need to worry about that. Yeah, so s is nothing but displacement, angular displacement, velocity, angular velocity, acceleration, angular acceleration. These terms are linear. Okay, and this one is angular. Okay, no? So now we will write that v is equals to u plus at, v square minus u square is equals to 2as, s is equals to ut plus of at square. So in terms of v, like v is the final velocity, na? So v is final velocity, u is initial velocity, and s is displacement, and a is acceleration. We will write that now. So in terms of angular means omega final will be equals to omega initial plus alpha t, right? And then omega final square minus omega initial square will be equals to 2 alpha theta. Okay, so theta is equals to omega initial into t plus of alpha t square. So this is the thing in terms of angular. Done? Can we go for the next one? Yes. So if you see here the same thing, na? So omega is equals to omega naught plus alpha t. Here omega final we have taken, omega initial they have taken as omega naught. Okay, no? So theta like is equals to omega t plus of alpha t square. So omega square, that is omega final square minus omega initial square equals to 2 alpha theta. Okay. Yes. Here is the question. First question: the angular speed of a motor will increased from 1200 rpm to 3120 rpm in 16 seconds, right? So the first question, what is the angular acceleration, and second question, how many revolution does the engine makes during this time? Okay. So first question we will see. So angular speed of a motor will increased from 1200 rpm to 3120 rpm in 16 seconds, right now. So initial angular frequency, which is nothing but 1200 rpm, I need to convert it into rps, like radians per second. Okay, divide by 60. So 0 and 0 will get cancelled off, and 1 times, and this is 2 times. So 20 radians per second. Yes, no? So I mean 20 into 2 pi into radians per second in terms of omega naught initial. Okay, so 2 pi v we will get. Okay, so omega, this is omega naught, then this is omega, this is final. Okay, this is the final. Okay, so final angular frequency, initial angular frequency we will find it, and we need to get the angular acceleration, which is nothing but alpha is equals to omega final minus omega initial by t. Okay, take a note of this. Done. Can we go for the next one? So how many revolution does the engine make during the time? Okay. So for those angular displacement in time we need to get it. So theta is equals to omega t plus alpha t square. Okay. So 45 into 16 seconds is the time, no, plus 1 by 2 4 pi 16 square. Okay. So if we solve that, we will get theta is equals to 1152 pi radians. So one revolution takes 2 pi radians. So divide by 2 pi, if we do, pi will get cancelled off. So 1152 pi divide by 2 pi. So pi and pi will get cancelled off. So we will get 576. Done. Can we go for the next one? Completer Abdul. Okay. So now we'll go for the topic work done by torque. So here let F be the force acting on a particle of a body at a point P. Okay. So with its line of action in a plane perpendicular to the axis. So in time dt, the point moves from the position P to P dash. So the displacement of a particle is ds is equals to dr into dt. Okay, r is nothing but ds by dt. Okay, so the work done by the force on a particle, which is nothing but work done, is equals to, we know that F dot S. So dw is equals to F dot ds for small work, small displacement. I mean small displacement, small work, right now. So dw is equals to F ds cos phi, cos theta. Okay, so dw is equals to F into r d theta, like in terms of ds, no, we will substitute r into d theta into sin alpha. Okay, so dw by dt is nothing but fr sin alpha, which is nothing but the torque. Okay, yeah. So why we have taken cos phi, why we have taken sin alpha, which is nothing but phi plus alpha is equals to 90. So phi is nothing but 90 minus alpha. So when I take here, no, cos 90 minus alpha is nothing but sin alpha. Done. So work done by torque, here it is nothing but dw is equals to tau into d theta. In the previous slide we have seen, no. So this is the work done by torque. So we know that power is nothing but energy, like work done by time or energy by time, no. So work done formula is tau into d theta. So tau into d theta by dt is the work, it's the power. Okay, it's not the work done. Okay, it's the power. Okay, so power is equal to tau into omega. So force into velocity is the one formula for power now. Right now work done by time is one formula and force into velocity one formula. So here tau into d theta by dt is one formula and tau into omega is the another formula. Like theta by t, no, displacement by velocity, like angular displacement and angular displacement and time is nothing but velocity, angular velocity. Done. Okay. Yeah. So work done by external torque increases the kinetic energy of a body. So the rate of increase in kinetic energy is nothing but d by dt of I omega square by 2. Okay. So of I omega square is the formula we have seen for the kinetic energy now for the rotational thing. So kinetic energy for rotational is nothing but of I omega square, right? No. So the rate of increase of kinetic energy will be equals to d by dt into 1 omega, I omega square by 2. Okay. So here we can take the expansion of the previous step and we will get the formula I omega into alpha. Okay. So the rate of work done is nothing but rate of increase in the kinetic energy, which is nothing but tau omega is equals to I omega alpha. So tau is equals to I alpha. So torque in terms of moment of inertia is the formula, that is tau is equals to I alpha. Completed. We'll go for the next one. Completed. Yes. Okay. So comparison of translation and the rotational motion. Translation is nothing but the linear, that is one dimensional. Okay. So linear motion, displacement x or s we have discussed. Okay, x, and velocity is nothing but dx by dt. Whereas we'll see like displacement x, angular displacement theta. Okay. Velocity v is equals to dx by dt, whereas angular velocity is equal, that is nothing but omega is equals to d theta by dt. Acceleration is nothing but velocity by time. Right now dv by dt, angular acceleration is alpha is equals to d omega by dt. So mass in this moment of inertia I. Okay, and f is equals to mass into acceleration. So in terms of mass I should consider moment of inertia. In terms of force I need to consider torque. In terms of acceleration, angular acceleration, right? So work done is nothing but force into displacement. Here work done is equals to tau into d theta. Okay. So kinetic energy of mv square, here of I omega square. In terms of m, moment of inertia I. In terms of v, angular velocity omega. So power is nothing but force into velocity. Here power is nothing but tau into omega, that is torque into angular velocity. Linear momentum P is equals to mass into velocity. Angular momentum L is equals to I into omega. Take a note of this. Done. Completed. Can we move? Can we go for the next slide? So have you completed the worksheet? Completed. Okay. So tomorrow exam is there, no? So come on time. Okay. So, motion. Okay, laws of motion is the topic for tomorrow's exam. Okay, so remaining topics you have taken: chemistry, botany and zoology. Okay, fine. Okay, we'll see a problem. A cord of negligible mass is wound round the rim of a flywheel of mass 20 kg, right, and a radius of 20 centimeter. Okay, a steady pull of 25 Newton is applied as the cord shown in the given figure. The flywheel is mounted on a horizontal axle with frictionless bearings. So first thing, compute the angular acceleration of the wheel. Okay, so here mass they have given, that is 20 kg. Right now radius they have given as 20 centimeter, which I need to convert into meter. So 20 into 10 power minus 2 is meter, no? So 0.20 meter, and the force they have given now, pull 25 Newton, right? Okay, so the torque will be force into the distance, like a position, no? Yes, 25 into 0.20, so which is nothing but 5 Newton meter. Okay, the moment of inertia of a flywheel about its axis is mr square by 2. So where mass is given as 20 kg and R we know that 0.2. So 0.2 the whole square by 2, which we will get as 0.4 kg per meter square. So torque is nothing but I alpha. So from there I can find the alpha, no? Yes. So torque 5 we know, and the thing moment of inertia we know that 0.4, right? So angular acceleration is 12.5 meter per second square. Okay, it is meter per second square. So plane was last exam, okay. This exam is about laws of motion, tomorrow exam, okay. So for the next exam it will be work, energy and power, okay. So can we go for the next part of the question? Complete it first. So cross verify the answer. Done. Okay. So next question is, find the work done by pull when 2 meter of cord is unwound. Okay. So work done formula, like it's unwound, no, unwound. Okay, unwound in the sense like work done by pull, unwinding 2 meter of cord is nothing but force into displacement. What is the force? 25 Newton, and displacement is 2. So 50 joule is the answer. So the next question is, find also the kinetic energy of a wheel at this point. Assume that wheel start from rest. So start from rest in the sense initial velocity will be equals to 0, no? Yes. So we know that r theta is equals to s. So where theta is nothing but s by r. So 2 meter divided by 0.2 will be equals to 10 radians. So omega square, like it is final, it is initial. Okay, omega final square equals to omega initial square plus 2 alpha theta, where omega initial is equals to 0, right? We have talked about initial velocity, no? So omega equals to 0, right? So omega will be equals to 2 into 12.5 into 10. So where it is 250 radians per second. Okay. So from that, kinetic energy is nothing but of I omega square minus of I omega naught square, like the change in kinetic energy. Okay. So this is final and this is initial. So initial obviously it is 0, right? I can neglect it out. So only the thing is final I need to find. So it is 50 joules. Done? Okay. Can we go for the next one? Yes. So conservation of angular momentum. So when there is no external torque acting, no, the momentum will be conserved, right? No. So when there is no external force is acting, the linear momentum is conserved. Whereas here, when there is no external torque is zero, then it is conserved. Okay, it's constant. The angular momentum is constant, we'll say. So angular momentum is nothing but I omega. So momentum formula mass into velocity, whereas angular momentum it is nothing but I into omega. No, so I omega will be constant. So I omega, which is in the initial case, will be equals to I omega in the final case. So I1 omega 1 will be equal to I2 omega 2. So the thing is, I is inversely proportional to omega. Okay, if moment of inertia increases, omega decreases. So in this case now, moment of inertia of 1 is greater than moment of inertia 2, but angular velocity of 2 is greater than angular velocity of 1. So when a girl stretched her hands, moment of inertia increases, angular velocity decreases, and vice versa. Okay. Done? Completed? Okay. Next we are talking about the rolling motion. So rolling motion is nothing but it is sum of translatory plus rotational motion. Okay, translation, that is linear, okay, plus rotational. So consider a rolling motion of a disc on a level surface. Okay, this is the disc, this is the level surface, a plane surface we are saying. At any instant, the point of contact that is P naught of a disc with the surface is at rest. Okay. So let VCM is nothing but at the center, velocity at the center of a mass which provides the translatory motion. Here it provides the translatory motion. The magnitude of velocity V1 at a point P1, okay, at the top of the point is nothing but velocity of center of mass plus R omega in this point. Okay, so or else we can say that it is 2 times of the velocity of center of mass. Okay, it is directly parallel to the level surface. Whatever the velocity is here now, in this point it is twice the velocity of the center of mass. Done? Can you go for the next one? Yeah. So kinetic energy of a rolling motion, which is nothing but kinetic energy of a rotational plus kinetic energy of a translation. So Kr is the kinetic energy due to rotational motion of a body about a center of mass, whereas Kt is the kinetic energy due to translation motion of a body. So we know that due to translation, no, it is half mv square. Due to rotation, it is half I omega square. So here we can expand the thing. Okay, I is nothing but mk square. Okay, mk square, which is in terms of radius of gyration we have seen. So k is equals to root over I by m, no? So where I is nothing but k square into m. Okay, so m into k square into b square by r square, which is nothing but v is equals to r omega, no, where omega is nothing but v by r. Okay, v by r. So v by r the whole square plus half mv square. Okay, so the final formula is k is equals to half mv square into 1 plus k square by r square. This formula is for the kinetic energy of the rolling motion. Okay. Done? Okay, so we will see the next topic. Yes. Yeah, equilibrium of a rigid body. So rigid body is said to be in a mechanical equilibrium if both linear momentum and angular momentum are not changing with time. Okay, so if net force on a rigid body is 0, linear momentum is constant, that is translation equilibrium will say, that is F1 plus F2 plus up to Fn will be equals to 0. Next point is, if net torque on a rigid body is 0, angular momentum is constant. Okay, first thing, net force, if 0 means linear momentum is constant. Next one, net torque on a rigid body is 0 means angular momentum is constant. So tau 1 plus tau 2 plus up to tau n, it will be equals to 0. In this case, rotational equilibrium we will say. Okay, two things, mechanical equilibrium means if both linear momentum and angular momentum are not changing with time, and then net force is on of a body is 0 means then linear equilibrium, like linear momentum will be constant. So net torque means and rotational equilibrium, that is angular momentum is constant. Okay. Done. Can I go for the next one? Okay. Okay. So here we are considering a rod of A, B and C, where A and B are the end point and C is the midpoint of the rod. So the total rod length is 2A. So from A to C it is A and C to B is A. So apply two equal parallel force at A and B, that is perpendicular to the rod. Moment of force at A and B are about C is nothing but A into F. So moment of force is nothing but it is torque. So torque is nothing but F into R, no? F into R. So F into R in the sense the force and the position from point A to point C. So from about a C is A into F or F into A for both the cases, right? So when moment of force at A tries to cause anti-clockwise rotation of the end, whereas moment of force at B tries to cause clockwise direction of the end. Okay, hence the net moment on the rod is 0, that is net torque will be 0. So both are in the same direction, there won't be any torque, hence system is in rotational equilibrium, no rotation. Okay. So tau is equals to 0 means, that is torque is equals to 0 means rotational equilibrium. When force is equals to 0 means translation equilibrium. Done? Okay. We go for the next one. So if you see here, anti-clockwise is taken as positive, clockwise is taken as negative. So anti-clockwise in the sense we will go in this direction, okay, and clockwise in the sense will come in this direction, right now. So like this means clockwise, in this direction means anti-clockwise. So net force on a rod is not 0, which means it is not in the translation equilibrium, not in the translation equilibrium. So object is moving, okay. So next one, reverse in the force of B, like A is in the same direction but B is in the opposite direction of A. So both the moment of force about C are clockwise. So one thing we can understand here, the thing we are considering, clockwise or anti-clockwise, the thing is which is the less distance, we should consider that one. So if I come like this, the distance will increase. So in this manner I can reach the point C. About that point I need to go. So this is clockwise or anti-clockwise? Anti-clockwise, right? No. So they have given it's not clockwise, it's anti-clockwise. Okay, anti-clockwise is positive. Yes, no. Clockwise is negative. It is anti-clockwise. You can take a note of this. This is not a clockwise, it is anti-clockwise. Okay, so positive. So this also going in the anti-clockwise direction. Hence it is not in the rotational equilibrium, right? So total net force on the rod is 0. Total net force on the rod is 0 means it is in the translation equilibrium. Okay, translation equilibrium, not in the rotational equilibrium. So here this force and this force are equal and get cancelled off. But the torque, it is trying to rotate it, no. So that it is not in the rotational equilibrium, but it is in the translation equilibrium. Okay. Done. Okay. So equilibrium of a rigid body, a pair of equal and opposite force with a different line of action is known as couple. Okay. In the previous case we have seen the example, two forces at the point A and point B, right? Now both are in the opposite direction, both are in the same direction. Second case is it is in the opposite direction. No, that's what, a pair of equal and opposite force with a different line of action. Different line of action means, so it's not acting in the same line of action, different line of action is called as couple, we will say. Okay. So for the couple, no, it should be equal, the force should be equal, first point. It should be opposite, second point, and the third point, it should not lie in the same line of action. So these 3 points are important when we can call as couple. Okay. So with this we'll end this session up to this topic. So we'll continue with the upcoming session in the next class. Okay, upcoming slides in the next class. Okay guys, thank you.